Welcome back, everyone. In this lecture, we're going to talk about linear regression analysis. This will be the first of two different lectures focusing on linear regression. We're going to start by showing a brief comparison of how linear regression is associated with ANOVA and how it also differs from ANOVA. We're then going to move on to discussing the three rationales for using linear regression, as well as when to use it. And then also we're going to finish up with a little bit of talking about the nuances of how we handle independent variables when they're at different levels of measurements within a linear regression analysis. So let's go ahead and get started. So both linear regression and ANOVA are part of what is called the general linear model. And this is a branch of inferential statistics that focuses on analyses when we have a continuous dependent variable. So all of the tests that we've gone over this semester utilize a dependent variable. So if you go back and look at our examples of the z-test for one sample mean, the independent t-test, the paired t-test, and the one-way ANOVA, you'll notice the outcome variable, the dependent variable, is always at that interval ratio level of measurement. It was a continuous variable. Regression also requires the use of a continuous dependent variable. And there is another branch of inferential statistics that's actually referred to as the generalized linear model that can handle categorical outcome variables or categorical dependent variables. But for now, we're going to focus primarily on when we have a continuous dependent variable. Another similarity between ANOVA and regression is the fact that both of them can handle multiple independent variables. When I introduced you guys to ANOVA in our last series of lectures, we covered the one-way ANOVA. And that one way was referring to the fact that we only had a single factor or a single independent variable. There are other forms of ANOVA that can handle having more than one independent variable, and these are called factorial ANOVAs. Now, you might ask, well, why is it important or not important to have multiple independent variables versus a single one? Well, if you think about it, if we're trying to explain human behavior or outcomes in the world, more often than not, there's not just one factor that influences an outcome. So even if it's as simple as me trying to explain why somebody gets a particular midterm score and somebody else gets a different one, it's not something as simple as, oh, their gender influences their midterm score, or how many statistics courses they have taken that will determine their midterm score. There are things we could go on for days. You know, how proficient are they in math? How many hours did they study? How often did they attend class? All sorts of other factors that can have an influence on an outcome. So that's one of the good things about ANOVA and regression is they can both handle multiple independent variables. But the key difference, and this is what sort of makes linear regression rise to the top as sort of being the gold standard of the general linear model, is the fact that linear regression can handle both continuous and categorical independent variables, whereas ANOVA is limited to only handling categorical independent variables. So what do I mean by that? Well, if you look back at our test, you'll notice when we did ANOVA, our independent variable had to be a categorical, an ordinal or a nominal level variable that usually would have 3 or more categories, but we didn't want to have 20 categories. It was pretty limited in how we would handle ANOVA. Linear regression allows us to introduce things like number of hours spent studying, which is measured on that continuous scale as a predictor variable. And that's what makes linear regression so important. All right, let's go ahead and move on to the next slide. So there are three main rationales for why we would even attempt to use linear regression. The first is similar to what we've done with our other inferential tests. It's to describe relationships, to find out whether or not some independent variable is associated with a dependent variable, some outcome, right? Whether there's a significant difference, a significant change, the basic things we've covered with hypothesis tests. And that's all we're getting at with that number one, the describing relationships. But one of the nice things about linear regression is it allows us to go a little bit deeper in what we find from our results. So when we look at number two here, it says test and examine types of relationships. And as you can see with the bullet point, whereas t-tests and ANOVA can be somewhat limited in types of association between variables that can be evaluated, linear regression allows researchers to examine a range of relationships. So we're not just looking for association. You can build models using linear regression that examine direct causation. Does A cause B? Indirect causation. Does A lead to B, which then leads to C? Or interactive causation. Does the impact of A on B change depending upon the level of some other factor? So with a lot of these things, this is where regression allows us to go deeper into our understanding of how various variables work together. And then finally, for number three, linear regression, and this is arguably in our field one of the most important, it allows us to develop predictive models. And as you can see that I've written here, one of the best uses of linear regression is to develop predictive models. And in our field, risk and needs, offender risk, offender needs are based upon regression models. If I want to predict what's the likelihood of somebody recidivating, what's the likelihood of somebody reoffending or harming a former victim, things of that nature. Linear regression allows us to do that. And we'll take a look at some of those examples when we look at the linear regression equation. And this will mainly be in part 2 of this lecture. So let's go ahead and jump back. All right, when do we use linear regression? Okay, this is the nuts and bolts slide, right? This is the one to make sure, do I know if it's appropriate to use linear regression? And here's what we got. The dependent variable, as mentioned earlier, we can only have one dependent variable, and that dependent variable must be continuous. So it must be at that interval or ratio level of measurement. Number two, when we look at the independent variables, this is the cool thing about regression. Not only can we have 1, 2, 3, 4, whatever, we can have as many independent variables as we want, but also we can have those variables at either the categorical level, the nominal or ordinal levels of measurement, or at the continuous levels of measurement, the interval ratio. And this is one of the things that, like I said before, and I'll stress it one last time, this is what makes linear regression sort of like the gold standard of what we've been trying to get to this semester, is because we can have one or more independent variables, and it doesn't matter what level of measurement that independent variable is at, we can introduce it into a linear regression model. All right, so but there is a caveat because we have to figure out how to treat those independent variables. So let's move on to the next slide. So far with what we've been doing with our analyses, was it the t-test or the ANOVA F, we just entered our variables into SPSS pretty simply, right? It didn't matter because they had to be categorical, either only two categories with t-test or 3 or more categories with F-test, and then SPSS for the most part did the rest of the work. That's not quite the same with regression. With regression, because it is based on a linear model, it is very closely related to that Pearson's R, that correlation coefficient that we talked about earlier in the semester. It's trying to draw a predictive line. Okay, so what does that mean? Well, it means that our independent variables have to be seen sort of like in a step ladder type approach, in a continuous approach. So if we have a continuous independent variable, we can leave that variable as it is in SPSS. So an example, if I'm measuring age as you're 22 years old, you're 31 years old, you're 43 years old, etc., we leave it alone. We just leave the variable as it is in SPSS, and it will work perfectly fine in our linear regression analysis. On the other hand, if we have a categorical independent variable, we have to make sure it is coded properly. So the simplest is if you have what is known as a dichotomous or two category independent variable, like a yes/no question, a male/female question, something where we're limiting our answer choices as being only one of two, like 0 and 1, we code those two categories of that independent variable and make sure that they are coded that way. So if I had a very independent variable that was gender and I limit it to only being male and female, I would want to make sure that one of the groups was coded as 0 and the other group was coded as 1. And therefore it'll work in the linear regression model. If I have an independent variable that has 3 or more categories or 3 or more levels, I need to do something what is known as dummy coding. So I need to dummy code that particular variable into k-1 dummy variables. And k in this particular example equals the number of categories or levels in the original variable. All right, so a lot of this, some of you may be going, I have no idea what he's saying. Bear with me, it'll start to make sense as we work through it. So the bottom line takeaway from this particular slide is when we're looking at our independent variables, if my independent variable is at that interval or ratio level of measurement, I just leave it as it is, and SPSS will handle it when I do regression, period. But on the other hand, when I do a categorical independent variable, then I may have to take a look at it and make sure it is coded properly. And that's where we talked about that dichotomous coding versus dummy coding. So let's take a little bit closer look at dummy coding. So let's move on to the next slide. So let's imagine that in my linear regression analysis, one of my independent variables is current offense. Say we're working with a sample of offenders, and one of the things I measured is their current offense. The way that the original variable is measured has 4 levels to it. It has property, violent, drug, or other. So it's a nominal level variable with 4 levels to it: property, violent, drug, and other. In order to make this variable work in linear regression, I need to do a couple things. First thing I need to do is I need to figure out which is going to be my reference category. So the reference category is usually the largest group or the most important group theoretically. So, and then this depends upon the topic, the variable, whatever you're studying, and doesn't have to be a guarantee like, oh, there's always a perfect reference category. You just have to pick one group is the takeaway from this. So all interpretations from your analyses will then be made back to that particular group. So for us, let's just assume for a moment that we choose violent as our reference group. So we're going to be comparing all the comparisons in our linear regression analysis will be made back to that violent group. What we have to do for linear regression is we have to dummy code. So we're going to create k-1 dummy variables. So if we had 4 levels in our original variable, so we had property, violent, drug, and other as our 4 levels, we need to make 3 dummy variables. So those 3 dummy variables are going to be property, drug, and other. The one that is left out was our reference category, violent. And you'll see how this works in just a moment, how it all comes together. So we're going to take the total number of levels of the particular variable, subtract 1, and you're going to make that many dummy variables. And those dummy variables are going to be what's actually entered into SPSS for your analysis. So property, drug, and other. How are these going to be coded? Let's take a quick look at them. Looking at number 1, property. What this is saying, if somebody in our sample, if their offense was a property offense, then they'll get a value of 1. Anybody else, drug offenders, violent offenders, other offenders, will all receive a value of 0 for this new dummy variable. So the dummy variable property, once again, if you're a property offender, you get a value of 1. Everyone else gets a 0. Looking at number 2, if you're a drug offender, you get a value of 1. Everyone else gets a 0. If you're the other category, then you get a value of 1. Everyone else gets a 0. So let's take a look at how that plays out with a short example. Let's move on to the next slide. So on this slide, what we have here is a table, which imagine we have a very small sample size. We have 6 individuals. In our original variable, so you'll see sort of to the left, the column that says original variable, it was current offense. So we want to use current offense as an independent variable in our linear regression analysis. But current offense has 4 different levels to it, right? It has property, violent, drug, and other. So in order to introduce it into linear regression, we need to dummy code it. So how do we take care of this? Well, we create 3 dummy variables. So we did that k minus 1 dummy variables. We kept violent as our reference group. And then we created a new property variable, a drug variable, and an other variable. For property, let's take a look at property. If somebody was a property offender, then they get a value of 1. If they were any other type of offender, they get a 0. So as we go down the list of our individuals in this example, you'll notice person number 1 was a property offender. So for that property dummy variable, they get a 1. The next person was a violent offender. Violent offender is not property, so they got a 0. Number 3 was a drug offender. Not property, so they get a 0, and so forth. When we then move on to the next dummy variable, which is drug, we did the exact same thing, whereas if somebody was a drug offender, they got a value of 1, and everyone else got a value of 0. And you'll notice that in our sample, the only person who was a drug offender was person number 3, so that's why they have a 1. Everyone else has a 0. And the same thing for the other variable. So how this works is rather than introducing one original variable into the linear regression analysis, we would actually, when working with SPSS, we would introduce the 3 dummy variables. And you may go, well, wait a minute, what happened to the violent category? The violent category is still captured. And the way it's captured is, if you'll notice, let's look at person number 2. Person number 2 was a violent offender. So how would SPSS or how would our linear regression analysis be able to recognize that person number 2 is a violent offender? Well, the way it works is you'll notice that person has a 0 for all 3 dummy variables. So if you have a 0 for all 3 dummy variables, you must be part of the reference group. And the reference group in this case happened to be violent. So we'll notice as you look across, nobody gets a 1 on a dummy for nobody gets a 1 for more than one of the dummy variables, right? If you're a property offender, you get a 1 for property and nothing else. If you're a drug offender, you get a 1 for drug and nothing else. But if you get a 0 for all 3 dummy variables, you must be part of the reference group. All right, so we'll leave it for there, and then we'll move on to part 2.